This video is going to be about benzodiazepines, common prescribed anti-anxiety medication, anti-seizure medication, and I'm going to try to explain how they really work. You probably, if you're watching this, are withdrawing from them, or you want to know more about them because you're on them, and you might have gotten a rudimentary explanation from your doctor or from another internet site. But I'm going to try and go in depth and show you how these drugs actually really work, why you might feel pretty severe withdrawal symptoms when you stop. And I just want people to understand that knowledge is power, and if you truly understand how the medication works and what it's doing on a biological, biochemical level, you might have a much better time getting off of them or managing them in your life. I'm not trying to knock medical doctors. They have a very hard job trying to diagnose and deal with 20 patients a day. But the fact of the matter is they don't really get a lot of background in pharmacology. A typical GP who may have prescribed you these medications, they really don't know how the drugs they prescribe work on a biochemical level. And that's just a simple fact, and it's sad and maybe a little bit of an indictment of our system, but quite frankly, they get 2 courses in pharmacology in medical school. And outside of that, they're depending upon just reading a little bit. And they get a lot of information, unfortunately, from drug reps who come in and tell them how the drugs work. And they don't have the time to do a lot of homework on their own. So you may have heard things about benzodiazepines, like they raise the level of GABA in your brain and help the brain better calm down by increasing the braking system. That's not really how they work. They don't raise GABA levels, and we'll get into all that, how they actually function to cause you to calm down and cause your brain to slow down. And when you understand how that happens at a biochemical level, you'll see very clearly why there's going to definitely be withdrawal and rebound anxiety associated with the usage of these medications. It'll make perfect sense. And when you see that, you'll know a lot more, and you'll feel a lot better about what you're going through. Okay, so we'll get into it. Okay, so benzodiazepines first hit the scene in the 1960s, and they were invented to replace barbiturates. Barbiturates were the central nervous system of choice prior to that, and they were the sleeping medications and the anxiolytics previous to the 1960s, and they were deadly. They are very easy to overdose on because, as I'll explain later and I'll start to draw out, they actually work better than benzodiazepines because they shut down the central nervous system signaling, but then they also block the excitatory neurons. And so they're kind of working on the front end and the back end, and they're very effective at shutting down the central nervous system. They also, as I'll show later, with the GABA receptor, instead of doing what benzodiazepines do, they bind to a different section of the GABA receptor, and they keep it open for very long periods of time, and it slowly reverses itself. So they're very dangerous drugs, and benzodiazepines were sort of invented as a way to replace these dangerous barbiturates. So in 1960, Valium and Librium were first on the scene, and in a way they were more safe. They cut down on overdoses quite a bit because it's actually difficult to overdose and die on a benzodiazepine alone. You're usually having to see it mixed with another central nervous system depressant because the way they were designed, benzodiazepines are difficult to overdose on their own. They're effective at shutting the central nervous system down, but they don't do it in a deadly way, the way barbiturates did. So you see that Librium and Valium hit the scene, and then drug companies, of course, saw how much money they were making for, I think Hoffman LaRoche was the the maker of Valium, and they wanted to join in, so they started making a lot of the common ones you see today, like Xanax, Klonopin, lorazepam, or Ativan. These are more popular. They work quicker. They hit the receptor a little harder. They get into the system faster, and they're generally can be considered newer and cleaner and more effective than Valium and Librium. So you see a lot of copycat drugs on the market, and likely you're going to have more experience with Xanax and Ativan. So we'll get into how they work. Okay, very briefly, GABA stands for gamma aminobutyric acid, and I just want to look at the chemical structure of this stuff first. It's a neurotransmitter, chief inhibitory neurotransmitter in the brain, and there's some old-fashioned language to understand the organic chemistry, but look, you have 4 carbons right here, so you get your butyl sort of group, if you will. So you 1, 2, 3, 4. And the acid part here is coming off of this terminal carbon. It's going to be a carboxylic acid, right? You have the OH group here, and then just your regular carbon. This doesn't exist, excuse me, I'm sorry. You have a carboxylic acid right here. Ignore that. Been a while since I've been in organic chemistry class. So, and then on the other end, you have your amino group, which is going to be your nitrogen. You got some unpaired electrons out there. And then you just have these carbons that get saturated with hydrogen. So, you look at this group here and this group out here. These are going to be your areas on this pretty fairly simple structure that are going to be interacting, that are active. You have an acid here. You have an amino group here. And this is a fairly simple neurotransmitter. There's plenty of it in the brain. It's got a pretty simple structure. And it's an acid because of the carboxylic acid, and it's an amino right here. And the gamma is just telling you what carbon the amino group is coming off of. And it's an old way of labeling it. You have 4 carbons in here. And the gamma carbon, it would be considered this one. And the amino group comes off of that. So it's gamma amino butyric acid. Butyric because 1, 2, 3, 4, and you have your carboxylic acid group coming off of there. So gamma amino butyric acid, GABA, gamma amino butyric acid is GABA. Okay. And understanding this is fundamental to understanding how benzodiazepines and the braking system in the brain works overall. Okay, and I apologize for the sloppy handwriting, but just trying to get a basic overview of GABA. We show you the structure. It's a neurotransmitter. It's the chief inhibitory neurotransmitter in the brain and central nervous system. So this is the neurotransmitter that's responsible for inhibiting the brain and the CNS, and it's sort of like it has been described as the braking neurotransmitter. It's also responsible for muscle tone, okay? There's a little bit of debate whether GABA blockade causes actual muscle relaxation or whether it's just a side effect of central nervous system depressants in general that the muscle tone reduces, but GABA does play a role in muscle tone that's being very much looked at and constantly described better in the literature. Okay, the GABA neurotransmitter bonds to 2 subtypes of GABA receptors of which there are many subtypes of each. So there's GABA A and GABA B receptors, and of each the GABA A and B, there are subtypes of those. There are many different types of GABA A receptors, and there's different types of GABA B receptors, which makes it complicated to try to understand exactly how these drugs work. It's why some benzodiazepines are a little more effective in certain areas than others, because they bond to different subtypes better, and we'll get into that a little bit later. Okay, the GABA A receptors are called ligand-gated ion channels, while the GABA B receptors are G-protein coupled receptors. People with biochemistry backgrounds will understand the difference between those two. Not super important for understanding how the drugs work, and you can get around that. You don't have to beat your brain up over trying to understand that. GABA receptors are expressed on neurons, and GABA itself is also produced by neurons. Neurons release GABA, okay? So they're the releasers of GABA and also the receivers of GABA. It's a neurotransmitter. It's being bantied back and forth between neurons. It's how they communicate. It's how they tell each other to speed up, slow down, release, cytokines, all the different types of things that these cells can do. Again, that can get pretty complicated. We don't have to go too deep into it. Just know that the GABA A receptors are the targets of the benzodiazepines, while the GABA B receptors are more the targets of muscle relaxers like the medication baclofen. Baclofen is used as a muscle relaxer. It's used for people with multiple sclerosis, and it bonds to GABA B receptors. And the GABA B receptors seem to have a little bit more to do with muscle tone than do the GABA A receptors. The GABA A receptors are certainly more involved with central nervous system braking and depression. And we'll get briefly into, we're going to look at mostly the GABA A receptors, and we're going to go off in that direction. The GABA B receptors don't have a whole heck of a lot to do with the benzodiazepines, because the benzodiazepines don't really bond or interact too much with the GABA B receptors, if at all, under most circumstances. So we're going to look at the GABA A receptors. They are the targets of the benzodiazepines. And again, GABA is the neurotransmitter. It's a chemical in and unto itself. Understand that. It's released by neurons. It builds up in the synapse of these neurons, and it can be taken up by neurons, and in general it will shut down these neurons and prevent them from firing, and we'll show you how it does that, and why benzodiazepines are effective, and why they end up having a nasty withdrawal effect. Let's get into that now. Okay, so we understand that there's a neurotransmitter called GABA, a very small molecule, and that it's the chief inhibitory neurotransmitter in the central nervous system and the brain. We also know that there are several different types of receptors. There's a GABA A receptor, a GABA B receptor, and that these receptors have different subtypes, and there are many of them, and it's quite complicated. And we're going to try to avoid getting into the different subtypes and their structures and the protein structure, because that could be a little in-depth. We don't want to go crazy here. But it's important to note that GABA is moving about. It's being deposited by neurons that are GABAergic neurons. They release it, they pick it back up, similar to serotonin and all the other neurotransmitters. It's the same, it's just a different neurotransmitter. It's GABA. And we're going to look at now the way that neurons communicate with each other to get a little bit of a clearer picture, and then we can really start to understand exactly how benzodiazepines work, and you'll get a much better understanding of why you get the withdrawal symptoms. So let's look at right now a neuron, the synapse, where these receptors are located and how they work and how they don't work. And let's try and get a good grasp of that, and then we'll get right into exactly how the benzodiazepines work. All right, so I apologize. This is very rudimentary, but here's a drawing of a neuron, two neurons actually. So there's two neurons here, okay, and they're communicating between each other at this little junction called the synapse. And this is a blow up of the whole thing. If you were to blow that little area up, you'd see these two parts. This is part of this cell, and this here is part of this cell. They're not touching, but they're very, very close, and this area in between is called the synapse. And lined on each synapse of each part of the cell are receptors. Here is where your GABA receptors are going to be on GABAergic cells. Okay, and these little dots here are going to be GABA. Now, there could be many other neurotransmitters and many other receptors in here. There's receptors for serotonin, for dopamine, there's receptors for norepinephrine, and all your classic neurotransmitters. But right now we're focusing on GABA, and we're focusing on the GABA-A receptor, okay? Don't forget there's GABA-B receptors in all different types, and they're all there, but we're going to just kind of zone out on those and focus on the GABA-A receptors and try and get an understanding, because those are the targets of benzodiazepines. Now, these two neurons here are communicating with each other, and they're getting signals through the synapse of whether or not they should fire or not. And by fire, I mean when they fire, they almost send a little electrical signal down, and also the nucleus may release chemicals that there may be cytokines being released. When they fire, they're doing their work. And if they fire repeatedly and there's no off signal, that's a state where you're going to have a seizure. If they're firing more than normal and not getting normal off-put signals or signals to turn off, that could cause maybe, say, an anxious state or muscle spasming if they're not getting the proper signal to turn off. So these guys firing without control, if they're firing and they're not getting turned off properly, in the worst case scenario, you're out looking at convulsions or seizures. In a more mild scenario, possibly racing thoughts, anxiety, and whatnot. So a popular target for this has been to try to find drugs that will get these neurons to slow down their firing rate. And how does that happen? Well, it all has to do basically with simple voltage and simple electricity. And I'm going to simplify this because I don't want to complicate and make this too hard to understand for people that are just trying to understand how their drugs work, how the benzodiazepines are taken work, and why they're causing withdrawal symptoms. So I'm going to simplify this greatly, and we're going to show another diagram here. But let's just say that if the inside of the cell is positively charged with respect to the outside of the cell's going to fire. Simple, basic voltage difference. Again, if it's negative on the inside with respect to the outside, that means, say, if there's more negative charge on the inside than there is to the outside, it won't fire. If there's a positive charge on the outside with respect to the inside, it will be in a state called hyperpolarization. If it's more negative on the outside than it is on the inside, it's going to fire. It's going to fire repeatedly. Again, I apologize. I might have gotten that screwed up in the first part. If it's negative on the outside with respect to the inside, that cell is going to fire. It's going to release cytokines. It's going to cause spasming, and if it continues to fire, it could cause seizures. Synapse, little area blown up, GABA receptors. Remember, GABA could turn these off. If GABA binds to its receptor, it's going to turn off these cells and stop them from firing. And the mechanism by which it does that is going to be simple voltage differences between the inside and the outside of the cell. And I'm going to go over that now, and I'm going to simplify it greatly so that it doesn't become too confusing for a simple sort of explanation that we're doing here. Okay, this is extremely simplified, so excuse me for being quite simple here. I just don't, like I said, don't want to confuse people. I want this to sort of be simple so we can get into how the drugs work. But so what I have here is just a very simple diagram. This would represent the inside of a cell here, this whole area. And this would be the cell wall. This is the outside of the cell. This here would be a GABA receptor, okay? And I'll show you a better diagram of one in a second. So what we just talked about, we have sodium ions that are positively charged, and we have chlorine ions that are negatively charged. So on the outside of the cell, if we look, we got 1, 2, 3, 4, 5, 6 negatively charged anions of chloride. On the outside, we also have 1, 2, 3 positively charged sodium ions. So if you look at it, you got a net negative 3, right? Because you have 3 more negatives than you do positives. Net negative 3. If you look at the inside, you have 1, 2, and 1, 2. You have 2 positively charged sodiums and 2 positively negatively charged chlorines. Now, in real life, there would be trillions of these anions, and this is just extremely simplified, just so you can follow along and get a grasp of how the receptor works, and eventually how the benzodiazepine is going to work. So we have all the charges are offset on the inside. The negative charges are all offset by the positive charges, and the outside of the cell is negatively 3. And we're being real simple here. In real life, we would measure millivolts by the aggregate of all of these charges, but we're just saying there's a negative 3 net charge, because there's 3 more anions than there are cations, or positively charged ions. And there's no charge here, they're all offset. So, like we said just before, the outside of the cell has a negative charge with respect to the inside, so it's going to fire. This neuron's going to fire. Okay? So how can we fix this situation if we don't want the cell to fire? We need to move chloride anions into the cell. If we can get 3 of these to move into the cell, the inside of the cell would have a negative charge with respect to the outside of the cell, and the cell wouldn't fire. That's where our GABA receptors come in, and that's what they essentially do. We talked about how they're ion-gated channels. So if you think of the cell wall here as a fence, one long fence, keeping everything out, and the GABA receptor is a gate that can open and close to let things in selectively. Now we're starting to narrow in on what this GABA receptor really does. So we want to move 3 of these chloride ions into the inside of the cell. This GABA receptor just so happens to have the molecular structure and the ability to move chloride ions. Only chloride ions are passing through. It can move chloride ions. It's a little chloride ion pump, and it can get the 3 chloride ions that we need to get in here through, if only we can open it. And you've probably heard of the lock key sort of description of a receptor. It's a lock, and it has a key. Well, in this case, GABA is the key. When GABA bonds to its bonding site on the GABA receptor, it will open and it will transport chloride ions through the cell wall until that inside of this cell wall, inside of this cell, becomes negatively charged with respect to the outside. And when it does that, the cell will shut down. Now, we're being real simple here, and we're just looking at GABA. In real life, GABA is doing its thing to pump in sodium or chlorine to make it more negative. There's also excitatory neurons or excitatory neurotransmitters like glutamate. They do the opposite. They try and reverse that charge and get the cell to fire. We talked about barbiturates in the beginning and why they're dangerous. Barbiturates turn on that GABA receptor, and then they also block the glutamate in a way, and they I told you how they kind of do it on both ends, and that's why barbiturates can be much more dangerous. So we start to see here that a GABA receptor's function, and we're going to look at them now in a proper diagram that I borrowed from a research paper, but its function is to transport chloride ions and hyperpolarize. When this becomes negative inside, it is called hyperpolarization. Hyperpolarization is the making of the inside of the cell negative with respect to the outside and stopping the neuron from firing. So a GABA receptor, when it bonds to GABA, opens like a little gate and allows chloride ions to get through and hyperpolarizes the cell. Let's take a look at a little bit more of a proper diagram as opposed to my chicken scratch. Okay, now we're getting somewhere. Here's a GABA A receptor. It's closed in this here, it's opened here. It's wedged in between the cell. This GABA receptor is encoded by genes, your genetics. And there's many subtypes, but it's made up of 5 different proteins that come in bonds together. You can kind of see that here. There's 1, 2, 3, 4 over here, and 5 over here. There's 5 different proteins that come together. Up here is just my little chicken scratch version of 2 neurons. Very simple. The synapse is here, and all the talking goes on between the synapse. And right in the synapse are millions and millions of these little GABA receptors. And when GABA bonds to the receptor, okay, at this site right here, this is the GABA binding site. That little molecule we talked about before with 4 carbons, 1, 2, 3, 4, and the carboxylic acid and the nitrogen group, and all of these hydrogens in here. That little molecule, GABA, when it bonds to its little receptor point open, it opens this gate, and you see chloride ions flowing through. The chloride ions flowing through to the inside of the cell, through this cell wall, this fence. This is a fence blocking everything else out of the cell. There's chloride ions out here. And there's also sodium, different other positively charged anions. When GABA bonds to that little receptor point, this is the receptor for GABA right here. GABA bonds to it, it opens. GABA bonds to its little receptor right here. Opens the cell. Chloride passes through. When it does that, it will hyperpolarize the cell and stop the cell from firing. This is taking place naturally inside you all the time. Your body is measuring how many of these neurons are firing, and it's releasing GABA and trying to maintain homeostasis. And when things get a little too fired up, there's plenty of GABA floating around in there, bonds and lets chloride ions through. And this is going back and forth to try and keep homeostasis. What they're showing here is different. This is where different drugs bond. Barbiturates we talked about before. There's a little binding site for barbiturates. If a barbiturate binds here in its spot, as opposed to GABA, It opens the cell. The chloride ions flow through like they're supposed to. It also does other things like we just discussed. It will prevent, like, glutamate or other excitatory ions, excitatory neurotransmitters from making the cell fire. Also, the barbiturate will keep this open for a very long time, like I said before, and that's why it's so dangerous. GABA it binds and then it leaves. It binds and then it leaves. So it opens and closes like a gate. Lets the dog in, lets the dog out. Kind of maintains homeostasis. If you take too much of a barbiturate, it'll bond to its spot right there, and it will keep this gate open for forever. And not forever, but for a very, very long period of time, and that can be dangerous. So they invented the benzodiazepines. And as you can see, there's something called the benzodiazepine bonding spot on a GABA receptor. And that benzodiazepine bonding site, it does something sort of neat. It acts like GABA. It's not GABA. But what it does, and this is important to understand, when the benzodiazepine bonds here, it doesn't open this. It doesn't open it. But what it does is it sort of just changes the conformation of this protein just a little bit so that GABA can bond to it much more easily. The barbiturate is kind of doing the same thing, but it's changing the conformation so much that GABA is just going to hit it like crazy. Whereas the benzodiazepine, it sort of changes the structure of this protein a little bit. So here's the closed protein, the closed receptor, benzodiazepine bonding site. Here's the GABA site. So say there was some GABA right out here, but it really couldn't get in there. It couldn't bond to its spot because there's just some stuff in the way here. And I'm being real simplified, and I'll get into this in the next diagram. But when the benzodiazepine bonds to its spot, it doesn't open it, but what it does do is it changes this protein a little bit. And we talked about how there's these little active sites on GABA. There's the nitrogen group and the carboxylic acid group. The rest of it's sort of dead weight, but these two spots can interact with other chemical spots. And the benzodiazepine, when it bonds, like I said, just changes this structure just so much that GABA can really get to its spot and bond very easily and open this receptor and let the chloride ions through. So, benzodiazepines don't act as a direct agonist. In other words, they don't bond to their spot and open the receptor. What they do is they bond and they make GABA bond to its receptor much more effectively. And the way this happens is sort of has to do with tertiary structures of proteins. So if you were to look at this receptor in real life, it's sort of a winding mix of proteins that are all kind of stuck together. If you think of the DNA helix, how it's turning around, well, it's sort of like that, except it's not a deoxyribonucleic acid. But it has that bonding spot for GABA, and that bonding spot can get kind of hidden a little bit. You can have other proteins, other things wrap around it so that it's not accessible to the GABA. But when that benzodiazepine bonds to its spot, it opens that up, and the GABA can find it really, really easily. And we'll get into a little bit more about that in this next slide. Okay, trying to explain here really how benzodiazepines truly work. We just went over how they sort of change the conformation a little bit of that receptor, and they try to get the GABA to bond more easily. So I mentioned what these receptors really look like, and here's sort of the cartoon version of it. Okay, with the GABA binding sites here. This is the benzodiazepine bonding site drawn here. Also, ethanol works on this receptor, barbiturates. And here's the overhead view, okay? These are the different proteins. I told you there was 5 of them. And there's the pore for chlorine to get through. So when it opens, the chlorine gets through that pore. And to truly understand how the benzodiazepine works, here's sort of, I drew the squiggly spaghetti version, what this sort of really looks like. The proteins are sort of in the way of a polymer, right? And they're long lines. And what I have here is, this is the GABA receptor, and here is a GABA molecule. And it's moving towards this squiggly protein. But what I've sort of drawn here in a different color is another part of the protein is sort of blocking it. And I'm kind of drawing that GABA can't find its receptor right here. So this is sort of a squiggly protein. In real life, it looks more like this, a squiggly protein, polymers of amino acids all joined together. And you have part of the protein folded over, blocking the receptor from GABA finding it. That's a little G in a circle. Sorry for my chicken scratch. This is the benzodiazepine receptor. No benzodiazepine is bound to it at this point. GABA's floating around in the synaptic cleft, bouncing off this receptor, bouncing off the receptor, not finding its binding site. So it has to find its receptor, and it has to find its binding site as well. Can't really do that. And in a natural state, this is sort of what's happening. Now, you take a benzodiazepine, you pop some Xanax or, for example, Ativan. It bonds to its site. We come over here. The benzodiazepine is bound to its site. And for chemistry reasons that I can't get into because it's just too complicated, it changes the conformation of the protein a little bit. See, this part right here is that part that previously was folded up and around, blocking off the binding site for the GABA. But once the benzodiazepine is bound to the benzodiazepine site, come up here and we'll look. This is the benzodiazepine site. It's changed the conformation slightly, and that little part that was blocking off the binding site has moved down, and now the bonding site is completely exposed, and GABA can find it. So benzodiazepines bind to the benzodiazepine site on the GABA receptor. They do not raise GABA. They do not make more GABA. They just change the protein conformation so that the existing GABA that's already there can find its receptor. They only make existing GABA bind better to its receptors. And again, when it does that, the benzodiazepine binds, changes the conformation. GABA finds its receptor much more easily. It opens, chloride ions flow through and shut down the neuron from firing. Now, this GABA receptor has points for ethanol, general anesthetics, quaaludes, barbiturates, benzodiazepines, flumazenil, which is an antagonist. Flumazenil is an antagonist. If flumazenil binds, it will block any benzodiazepines from binding. So flumazenil is just an antagonist, and it can be used to reverse benzodiazepine overdose. If you take it, it will go in there, kick the benzodiazepine out of its receptor site, and reverse the conformational change so that GABA can't really find its receptor as easily anymore, and you return to a normal state. So this right here you might recognize. This is otherwise known as Ambien, the popular sleeping medication. So pharmaceutical companies have played a little trick. Since Ambien binds to a little bit of a different site, and it's not technically the benzodiazepine site, it's a little bit lower, it's not classified as a benzodiazepine. They call them Z drugs because they bind to a little bit of a different site on that GABA receptor. But they kind of do the same thing. They change the receptor's conformation, and GABA binds much more easily. So they do sort of the same thing as a benzodiazepine. Essentially act the same way. They just have a shorter half-life. They get in and get out quicker. But they do the same thing. They cause hyperpolarization of that cell and shut the neuron down from firing. Again, benzodiazepines work. That green little arrow right there is the benzodiazepine bonding site on this sort of squiggly line interpretation of a protein. The GABA binding site on the GABA receptor, this is all the GABA receptor, this is the GABA binding site. It's just not accessible because there's some protein stuff in the way, and it's folded up in there, folded up away. Benzodiazepine bonds. That folds back down in a little bit of a different direction, and now GABA can find its receptor. This is how benzodiazepine drugs work. Now, we're going to discuss briefly the different subtypes here. You see these different alpha, beta, gamma proteins. There are different subtypes of GABA A receptors, and different benzodiazepines have different affinities for them. This is why something like Valium is a better muscle relaxant than Xanax. It has slightly different affinities for slightly different subtypes of the GABA A receptor. We'll talk about that briefly. Okay, so we see now the full picture of how benzodiazepines work, and we can sort of understand why withdrawal from these drugs is so troublesome. And if you're watching this because you're going through withdrawal from a benzodiazepine, or you're taking them and beginning to feel ill, I'll be very brief in surmising why this happens. We talked about the GABA receptor and how it's composed of 5 different individual proteins. Well, each one of these proteins is the result of gene expression. They're genetic. They're proteins that are made by the expression of specific genes. I believe there are 19 different genes that code for the GABA receptor. I'll have to check that. But what happens essentially is when you take a benzodiazepine and it has its end result, as we discussed and showed, that it modifies the GABA receptor, there's a great deal of GABAergic signaling, and a lot of neurons do not fire. They're hyperpolarized, as we discussed. And the net result of that is that your body is smarter than the drug companies. Essentially, what happens is it detects the excessive signaling through chemical means. It detects excessive GABAergic signaling, and it ultimately sends a signal back to all the way down to the hard genetic expression, the hardware, if you will, the genes themselves. And it tells them to stop expressing the proteins that make the GABA receptor because there's too much signaling going on. So over a course of a couple of weeks, your body stops expressing these GABA A receptors. It stops expressing the proteins, and the net result is you end up with less of those receptors being expressed on the neurons in the synapse. And even though you may have the same amount of benzodiazepine in your blood and the same amount of GABA, now there's less receptors, so you have less signaling. And the more of the drug you take, the more this will fight back. Your body will also start to express more of the excitatory neurotransmitters and more of the excitatory neurotransmitter receptors. So essentially now, you end up with less and less GABA A receptors, more and more excitatory receptors, more and more excitatory neurotransmitters. So the 1 milligram of Xanax that you took in the beginning that put you to sleep, 6 weeks later, now you're taking 2 or 3 milligrams and you're getting almost no response from it. And if you try to stop, the little bit of GABA receptor that is left no longer has the potentiator, and it becomes less effective. You have less receptors, more excitatory systems in place, and you set yourself up now for a situation where you're going to have excessive firing of these neurons. They're going to fire excessively, and you're going to suffer rebound anxiety, rebound insomnia, muscle twitches, cramping, muscle shaking, spasms, possibly. In a worst case scenario, you could end up with a seizure from withdrawal of benzodiazepines. It's not as common as is sort of suggested, but it does happen. You can end up with convulsions or seizures from withdrawing from these drugs. But you can see that it's really tied back into genetic expression of these proteins. You're training your body as you take the benzodiazepine, you're telling it to make less and less and less of the GABA receptor. So if you're in an anxious state to begin with, you may be in a situation where you have reduced GABA signaling through that receptor. The benzodiazepines help for a brief period of time, but what they end up doing in the long run is leaving you worse off than when you started. After a mere 6 weeks, you can end up with less GABA receptors than what you started with, and you may have already been diminished in the beginning. In order to treat benzodiazepine withdrawal or to get off of these drugs, there's several methods that you could choose. One is to take a less potent, lower dose of a longer-acting benzodiazepine like Librium or Valium. Librium would be best. Stays in the blood for quite some time, and it acts on the receptors slowly over time. Doesn't have as dramatic of an effect. But eventually you're going to have to come off all benzodiazepines, at which case there are medications like gabapentin and anticonvulsants, stuff like Lamictal or even Lyrica. These anticonvulsants, and there's a lot of confusion around how gabapentin works because it's a GABA analog. It was designed to be a GABA agonist and to act at the GABA receptor. However, it does not do that. It failed in its mission. Gabapentin actually works on voltage-gated sodium and calcium channels primarily. There's some evidence that it may raise GABA levels, but that's debatable. A lot of the anticonvulsants work on the voltage-gated sodium channels. So in other words, they start trying to do the opposite, or they try to stop the positive cations from polarizing neurons. So they try to achieve hyperpolarization via a sort of a different mechanism. They can help reduce symptoms slightly, but they don't really help a whole heck of a lot, as most people would probably attest to. It's difficult to get off benzodiazepines. It takes quite some time, and you really need several weeks before that gene expression. The good part is that as you have excessive excitatory signaling, your body detects that as well, and it starts to tamp that down, and it starts to re-express the GABA receptors. But it takes weeks, if not months and months, for the body to rebound and start to express those proteins again and start to express those receptors in a normal way. So, it takes some time to get over benzodiazepine withdrawal. For those of you who watch this to try and get a little bit of a better understanding, I hope that it helped. You understand how those receptors work, now how benzodiazepines work, the method by which they work. You understand a little bit more about the GABA receptor, and hopefully that can help you mentally as you try to get over this or get off these medications. Or if you're on them now, maybe you might want to get off of them before you get yourself into trouble and before your body adjusts itself to compensate for the excessive signaling, the excessive GABA signaling. Some people have asked whether a GABA B receptor agonist like baclofen that we discussed briefly would be helpful. I'm not sure. Not sure whether baclofen could have any effect. It might reduce some muscle spasming, but it's working on a different receptor subtype, the GABA B receptor subtype. So you're still going to be deficient in the GABA A receptor subtype signaling. So you're still going to suffer some symptoms. It's going to be uncomfortable no matter how you look at it. There's some supplements out there that have been discussed, like valerian root, kava. The research on these has shown that their mechanism of action is by maybe acting on the GABA receptor in a different binding site. They don't work on the benzodiazepine binding site, so they won't have direct relief or direct activity on the benzodiazepine site, but they may block some of the positive cation channels. They may, taking a large enough of a dose might end up in a net result of some hyperpolarization of some of the cells and offsetting some of the discomfort. But any way you look at it, you have to let your body return to normal at some juncture, and that's going to hurt. And I hope you get through it. You will get through it. Pray. Prayer really helps. I highly suggest prayer to get through those difficult times. And you can do it. You will do it. Time goes by, and every minute that goes by, you're getting closer to returning to some level of homeostasis. Get yourself out, try and walk. Don't overdo it in the beginning, but you'll be okay. We're going to do opiates next. That's a real interesting subject. It's a lot more complicated than benzodiazepines because they work on so many different systems, and it includes the GABA system, and they work on a lot of different other systems. So they're more, benzodiazepines are kind of narrow in their effects, so they're kind of easier to describe. But opiates will be next, and I'm here to talk to anybody that would like to discuss it or would like some help. You can give me a call, 484-707-1281, and good luck to you. And I hope that the video helped. Take care.